Dear Professor and classmates, our group name is Project 2 Spect Apes, and our ongoing project is unsupervised semantic scene detection using β-VAE. Scene detection is the task of dividing the frames of a given video into semantic scenes and can be automated with the aid of CV techniques. Earlier work in this domain relies on threshold-based algorithm and supervised multimodal learning. However, there has been no attempt as we know to approach this challenge using unsupervised learning. In our project, we use β-VAE to detect scenes with unsupervised learning methods. β-VAE has an encoder to get latent distribution and a decoder to reconstruct the image. We improved on the original β-VAE and used the Nava dataset for training without any label. For all 192,000 framed Nava images, we reserved the first 31,000 images for validation and the rest for training.
Here is our overall approach. We first preprocess data and change its resolution. Then we use β-VAE to perform unsupervised learning on input images. We first use a CNN to encode images and learn the mean and variance of a Gaussian distribution to get disentangled features. Then we use a transposed CNN to decode latent variables and reconstruct images to calculate loss. To detect scene changes, we mark a scene change when the distance between two latent variables is large enough. The disentangled latent variables are expected to change sharply on scene changes, so the result could be better than using original images. We also extend β-VAE with different structures. For example, read one window of images at a time instead of one single image to capture context information of images. In this case, an RNN may be used to process input images before the CNN encoder. Here is the specific structure we use. We use 5 convolutional layers with batch norm and leaky ReLU to encode images. Then flatten the result and fit it in 2 linear layers to get mean and variance of latent variable. Then we use a 5-layer transposed CNN symmetric to encoder, followed by 1 convolutional layer to decode the latent variable and reconstruct image. To measure the distances between latent variables, we use Wasserstein distance, since they conform Gaussian distributions.
We use 2 ways to modify our models to include the context semantics. The first is called many-to-one. They input a window of the JSON image to get their features respectively, and use Foley connections to ensure the latent vector includes the context information. Another method is called sequence-to-sequence models, which use RNN after CNN, as what we do in homework 3. The β-VAE multiplies the KLD loss with beta as H loss here. And there is another refined loss called B loss to prevent the KLD from being too large. We will show that this increases the robustness of disentanglement capacities. Some results are listed here. This suggests that the optimizer and the different structure does not significantly influence the accuracies. Besides, the refined loss can improve the results, although it gives worse reconstructions. Last, the increase of dimension of latent vectors does not help with the accuracies.
To verify whether our models have learned to extract scene semantics into latent dimensions, we use TSNE to visualize the encoded latent parameters of each frame and label by scene ID. As you can see, since TSNE preserves local similarity, and most of the scene indeed stays in its own cluster, this means our model is learning. However, there are some scenes that are clustered together in the middle, and thereby harder to distinguish by our model. One surprising thing we found is that better details in the decoded image does not equal to better scene semantic disentanglement. Take these 2 models, for example. The model on the top has better accuracy for scene separation. However, its decoded image looks nothing like the encoded one. We think this is some kind of overfitting, as the lower model has much higher KL divergence. In conclusion, β-VAE is able to disentangle scene semantics without supervision. However, our architectural changes didn't necessarily result in any improvements, but we will continue to explore ways to improve our model. Most of our models are trained within 30 epochs, indicating fast convergence. Therefore, Our model is an efficient and cheap way of labeling things automatically. That's all for our presentation. Thank you.